Morning, everyone, and welcome to the JKMRC Friday Seminar series after 2 weeks of break. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respect to the ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australia and the global society. It's my great pleasure to welcome Max Zanin, who is online today.
Thank you.
Max is a mineral processing engineer with over 20 years experience in research. Through his dual role as managing director of MZ Minerals and an associate professor at the University of South Australia, Max developed high international recognition among both global mining industry and academia as a flotation expert. Today, Max talk will be about flotation circuits and new technologies. Does one size really fit it all? Please join me in welcoming Max.
Okay, thank you very much, Belson, for the nice introduction. And good morning, everyone. I'm very pleased to be with you this morning for hopefully some interesting discussion. So the presentation I'm giving this morning is basically an overview of some of the emerging new flotation technologies, but it will also be a discussion based on my personal experience on the adoption of new technologies within the mining industry. So it's not going to be too technical, also because it's 9 o'clock in the morning, actually 8:30 in Adelaide. But still, I hope it will be able to generate some interesting discussion later on. Wait a second, I'm trying to move to the next slide. It's not moving on my screen. Sorry, Belson, are the slides changing on your screen?
Not here.
I'm blocked. Let me try to stop sharing and share again. Sorry about that. It was working before. Share. This one. Share. Full screen. Okay. Okay, it works now. Okay, sorry about that. Just a very brief introduction about myself for those of you who don't know me. I know a few of you, but some may not. So I was born and raised in Italy, which is where I did my studies in mineral processing engineering. And after that, I also enrolled in a PhD, where I actually developed my interest in flotation. So I started very early. Flotation was through my career all my life. And back then it was interesting because I was doing flotation of plastics for recycling. So you may want to know that you can also use technologies developed for minerals for some other applications. And one of that is recycling. And it was quite successful in separating different plastics by using flotation. So that's where I started looking into flotation. But after a few years, I got the opportunity of moving to Australia in an institute which back then was one of the leading institutes for research in flotation, which was the Ian Walk Research Institute with John Ralston and Steve Grano. And so I decided to catch a plane and move from the University of Trieste in Italy, where I was, to Adelaide. And as you probably can tell, moving from that landscape to that landscape requires some strong motivation because Trieste is a wonderful, wonderful city. But the motivation was scientific research. So the opportunity of doing research in a leading institution was the driver for me to move to Australia, where I developed my career, my entire career in research and also as a consultant for the mining industry. So I started as a research fellow up to associate professor at the university. And in 2017, I also started my own consulting business through MZ Minerals Consulting, through which I really passionate in technology transfer to the industry. So all the major outcomes from research, to see them in practice and transfer to the industry. So I have this dual role now. So I have about 25 years of experience in flotation, and most of it around copper flotation. And I also have previous history of some collaboration with you guys, with the JK, because at the early of my career, I was working on one of the Amara projects, the Amara P541 on flotation froths, which was a joint project between the JK and the University of South Australia. And then I also been for many years one of the leaders of the Amara P260 project on flotation, with Steve Grano first, and then with Bill Skinner. And lately, I'm also been involved with the brief research consortium at the University of Adelaide, which is called Unlocking Complex Resources Through Lean Processing, which is mainly based on big data analytics and advanced mathematics to optimize the mining cycle, and in particular, mineral processing, so grinding and flotation. So this is where I stand. And today I'm going to discuss about some of my findings in my relatively long career, and some of my impressions about new technologies and how they apply or can apply to the flotation plants, grinding and flotation. So you all probably know very well that the mining industry is facing some challenges now, which basically arise from the scarcity of high-grade and very good deposits. So high-grade deposits have progressively been depleted, and now we need to face mining deposits which are very low-grade or difficult to mine or expensive to mine and to process. And therefore, there is a need to economically treat low-grade and difficult material. And when I say economically, I mean we need to be energy efficient, so consume less energy. Energy, you know very well, it's becoming more and more expensive in several parts of the world, including Australia. Water efficient, so we need to use as less water as possible, and possibly reduce the footprint of plants and concentrators in order to reduce the overall capital and processing cost. So these challenges became a driver for the development of new technologies. Because as you can imagine, to make things more efficient, I need something new, something more advanced, to be able to produce a high concentrate grade at high recovery with reduced processing cost. And this is why over the last, let's say, 10 to 20 years, several new technologies were developed, in particular for flotation. Now, before moving to those technologies, it's important to understand what happens in flotation, in a flotation cell. And this is something that I guess you guys should know very well, because most of the early research in the hydrodynamics of flotation come from the JK. So if you go back to your publication from a few decades ago, everything is about flotation hydrodynamics and how to correlate the flotation kinetics to hydrodynamics and gas dispersion. But to make it very simple, what happens in a flotation cell, you have bubbles, you have particles. Particles attach to bubbles and are transported to the flotation froth. So the mechanisms are collision between bubble and particle, attachment, which is where hydrophobic particles attach to bubbles, and then detachment, which is when, because of turbulence, coarse particles which have high inertia tend to detach from bubbles. The overall flotation rate depends on the balance between these three sub-processes. So collision, attachment, and detachment. So because of that, in a typical mechanical flotation cell, there is an inherent, let's say, low efficiency in the recovery of coarse particles and fine particles. So if you look at this plot, on the right plot here, which is a very famous so-called elephant curve developed by Lynch, which shows the recovery by particle size in flotation in a number of different flotation plants. you can always see that there is an optimum particle size range where flotation in a mechanical cell is very efficient, let's say from 10 microns to 100 microns in general. But as you move finer or coarser, the recovery drops. So the efficiency of flotation drops. And we know that the low recovery at the fine end is due to insufficient collision energy because there is not enough energy when fine particles collide with bubbles. While at the coarse end, it is because of excessive turbulence, which causes detachment of the coarse particles. So you can try to optimize things, but there is always a trade-off between fine and coarse recovery. So mechanical cells work very well in a defined particle size range, but they tend to lose efficiency as you move coarser or finer. So in order to address this, there is a need of something different, of new flotation technologies different from a mechanically agitated cell. But if we look at the mechanical cell, we need to say a couple of things. Mechanical flotation cells are relatively old as a technology. They were introduced more than 100 years ago. You can see those photos there. That was an early bank of flotation cells in 1920. But the basic principle is always been the same. So you have a tank, you have an impeller, you keep your particles in agitation, and you purge air bubbles into the system to collect those particles. So the design criteria haven't changed much in 100 years. However, some major improvements happen over time. The main difference now is that the size of flotation cell has been increasing remarkably with time. So from the early days where one flotation cell had a volume of a few cubic meters, now we are at 700 cubic meters, so they're much larger. And larger cells are more efficient in terms of energy, so you have a lower specific power consumption. So they are cheaper to run. But at the same time, you can't keep increasing the volume indefinitely, and mixing becomes difficult as you have larger and larger volumes. But in general, mechanical cells are very reliable because they are easy to operate and operators are trained on operating them, and you don't get major surprises when you run a mechanical cell. But as I said, they tend to be inefficient with respect to particle size, with respect to energy, with respect to water and air. Nevertheless, within a few decades, there has been a significant improved design for mechanical cell as well. So this photo here is taken from Ethel Schmidt, but it's just to show that there has been a lot of work around the engineering of impellers, of air dispersion within the cell in order to optimize things as much as possible, to keep particles suspended, avoid sanding in the cell, and provide good gas dispersion. And at the same time, a lot of work has been done around the design of froth crowders, cell launders, so we can handle the froth much better now than 50 years ago. And therefore, the overall efficiency of mechanical cell is much better now than what it was just 20 years ago. So something is definitely good in that space as well. But still, as I said before, the question is, does one size fit all? Or, I mean, does the mechanical cell, is the mechanical cell the optimal device over different mineral systems, or over different particle size ranges, or several different things? Because in a flotation cell, we have a number of different particles. We have fine particles, coarse particles, fully liberated particles, or particles with very little liberation, which are mainly locked. So is the mechanical cell the best device to recover all of these particles at the same time? And the answer is probably no, it isn't. So there is a need for dedicated technologies, dedicated cells, which are completely different from mechanical agitated cell, or at least different, specifically designed to treat fine particles and coarse particles, as an example. And at the same time, in order to reduce energy and water consumption. So selectivity is probably the key for any new technology which is developed to improve flotation. So there is no best configuration which fits all. You need to design a flotation device for the specific particles and minerals that you want to recover, if you want to be very efficient. And just a quick overview of some of them, which are now consolidated by used to be emerging technologies. And the first coming to my mind is pneumatic cells, like the Jameson cell, which is very famous. So in pneumatic cells, basically, the slurry is fed to the flotation cell through a downcomer in a condition of high energy and high shear, and therefore there is a much improved collision efficiency between particles and bubbles, and therefore you can get much better recovery of fine particles in particular compared to mechanical cells. So you can have high throughput, more efficient collision, and more efficient recovery of fine particles. And I added a note there that the first Jameson cell was installed in 1989, so several decades ago. And I will go back to this point later on in my discussion, because one of the interesting things is how long does it take for a new technology to become proven and become applied everywhere? How much time does the mining industry take to take something from the early development to something which is basically a standard? And it's very interesting. We will discuss this later on. So nowadays, the Jameson cell is a proven technology. There are more than 400 installations around the world, and it's basically universally accepted that they can replace mechanical cells very efficiently, in particular in cleaning stages. So you can replace a number of mechanical banks of cells with just one Jameson cell. So they can operate as cleaner scalper, cleaner or recleaner, produce the final concentrate directly. They are very flexible, and everyone uses them now in designing cleaning circuits. They are very efficient. One other relatively new technology is from Aries. Now, I'm not biased against for Aries versus FLSmidth or any other Glencore. I'm just presenting some of the emerging technologies without promoting any specific supplier, of course. And the interesting thing about the stack cell is that it's more similar to a mechanical cell, a traditional cell, but all the agitation happen in a confined chamber inside the flotation cell. So you just need to agitate with very high turbulence a smaller volume of slurry. And this makes it more energy efficient. So you don't need to agitate larger volume of pulp. So you consume much less energy. And at the same time, you have better collision, more efficient collision, and a large volume of the cell where the slurry is less agitated. And therefore, you can disengage the hydrophilic particles. You don't have so much detachment of the coarse particles. And on overall, you can get better recovery and grade across different size ranges. So not only fines, but also at the medium to coarse end. They are more efficient than mechanical cells, the traditional mechanical cells. So they are also being installed more and more, especially in the last few years. They've been developed in the early 2000s, but their adoption is growing as we speak, I would say. And then we have fluidized bed flotation that you guys know very well. In particular, Benson knows it very well because he developed his own career around fluidized bed flotation. And I mentioned the Aries Hydrofloat here, which was developed in the late 90s. By fluidized bed flotation, you can have definitely an improved recovery of very coarse particles because it's completely different from a mechanical agitated cell. Basically, in fluidized bed flotation, you generate a fluidized bed of coarse particles, which stay suspended, but they are not heavily agitated, so there is no turbulence. And so there is a chance for multiple bubbles to attach to the hydrophobic particles and very gently lift them to the cell launder. So you prevent detachment because there is no turbulence. That's the very big advantage of fluidized bed flotation. So because of this, you definitely have superior recovery of the very coarse particles. And this is just some experimental results. And these are actually from a real copper ore. So it's not single mineral work, it's the copper ore. And you can see that if you compare the recovery mechanical cell to hydrofloat, particles as coarse as 300 microns, they go from 20% recovery in mechanical cell to more than 80% recovery in hydrofloat. And these are not fully liberated, it's just composite particles, very coarse. You can recover them very well because, as I said, you have no turbulence and you can have multiple air bubbles attaching to those particles. So the good side is, yes, you can definitely have good recovery at a much coarser particle size, which means that you can grind much coarser and it costs you much less energy to produce your flotation feed. So you have a huge reduction in energy because you don't have to grind very, very fine. So one possible application of coarse particle flotation is performing primary grinding coarser than usual. So talking about copper flotation, normally you grind at 150 microns P80, 150, 180, depending on the ore. Let's say if you want to implement hydrofloat, you can afford to grind at 250 or more P80, so it's cheaper. You perform rougher flotation, and then you can introduce fluidized bed flotation to treat the rougher tailings. The only difference from the typical flotation flow sheet is that the hydrofloat requires you to remove the fines because it doesn't like fine particles. So you need to introduce a desliming stage where you remove the fine particles from your tailings and you process as the coarse fraction in the tailings in hydrofloat and produce a coarse concentrate. After which, it's highly desirable to treat the coarse concentrate separately, so you need to regrind that and float it in conventional cells. So this flow sheet is proven to produce advantages in copper flotation. It's now been tested in several different operations, and therefore I will say that fluidized bed flotation is something that we will see more and more in the future design of flotation plants, as well as a Jameson cell for the fines. And now I just want to mention another two most recent technologies that both come from FLSmidth. And one of them is the reflux flotation cell, and the other one is called coarse air flotation cell. And they both combine flotation with the principle behind the reflux classifier, which is the boycott effect. So to make it simple, it's just a series of inclined channels. And because of that, the boycott effect means that you can help settling and disengagement of fine particles. So they settle much better than they normally do in a vertical cylinder, as an example. So combining these channels to a high shear flotation device, we have the reflux flotation cell. So there is a downcomer similarly to a Jameson cell, but then you also have this bottom part of the cell, which has the inclined channels, which help removing fine gangue and therefore producing a higher grade concentrate. And few of these are being tested now and about to be implemented here and there in different concentrators. The other one is very interesting to me, but I never saw one actually in action, and combines fluidized bed flotation to the boycott effect to the reflux classifier. So the claim is that you can have the same recovery that you have in typical fluidized bed flotation, but at the same time you can improve grade by assisting rejection of fine particles which are unselectively reported to the concentrate otherwise. So it's a very interesting concept to me, the coarse air, and I'm really keen on seeing one running soon because it's very interesting to me. Now, after this quick overview, based on all of these new technologies which are emerging, how can the new flotation plant of the future be? How will it be when we design a flotation plant thinking ahead, a little bit different from what's done today? So I can see that in the flotation plant of the future, there will be a lot of modern technologies dedicated to treat separately fine particles from coarse particles, as an example. So we'll see more and more Jameson cell and stack cell, reflux flotation cell, hydrofloat, together with mechanical flotation cell, taking over from some specific applications where mechanical cells are not too efficient. But at the same time, there will be a lot, and I said a lot, one more, of new process control. So real-time pulp chemistry. There already is a MegaPulp developed by Megato, by which you can in real time measure the EH, the pH of your pulp, but also dissolved oxygen consumption, and therefore you have an idea of the pulp reactivity in real time in different parts of the circuit, which is very critical for flotation. Then there will be more of inline particle size analysis, so particle size in real time in different points of the circuit. The use of acoustics, vibration monitoring for the health of mills, but also roping of cyclones or so many other things. So there will be a lot of new sensors and technology to control the flotation plant. And finally, a lot of advanced mathematics, AI-based mathematics, machine learning, to collect a lot of data from the plant and be able to be predictive and optimizing condition using advanced mathematics. That will definitely be there. But the question I was asking before, how long will it take? How long does it take for new technologies to be adopted, in particular by the mining industry? Well, I'm presenting this graph here because it's very interesting. It was developed by Gardner and then Rogers and Moore, which shows the correlation between the expectations in a new technology and the rate of adoption by the industry. So at the top there, I'm sorry, I can point it with I can now, yes. We have here the invention of a new technology. Let's say I invented the Max Zanin flotation cell, and I can show from my lab experiment that it produces amazingly good results and can have very good flotation recovery, much better than anything else. And therefore the expectations go high, very high and very quickly because of my claims. And very often, if not always, the expectation raised to and are inflated to a very unrealistic level, so much higher than what the technology can actually do, because there is a lot of enthusiasm around it. And at this stage, there is a rate of adoption which is growing, but it's still pretty low. Still, the big companies are not jumping on technology, so just innovators are trying to adopt it and test it, so very little adoption rate. At this stage, it always happens that you realize that the technology is not, in brackets, as good as it was initially claimed. So there are some problems, there are some difficulties in operating it in plant scale, at larger scale. It's not as easy as we initially thought, and therefore there is a sudden drop of expectations, and which is as fast as the initial raise in expectation. So you go down to a level which is below what it's reasonable to expect from the technology, so you become more and more skeptical. And at this stage, the rate of adoption is critical. It's where just early adopters still believe in the technology and they keep implementing it. And it is the most critical step for a new technology to become then eventually consolidated and universally adopted. Then when you show that the technology actually is doing something good and therefore is producing some results, it's where the majority of the industry is jumping on it, is implementing it and installing it in the flotation circuits, flotation or any in the process. And therefore, you have an increase in the expectations, which is now realistic, it's not inflated, and you have the majority of companies installing it until you have a slow decline with time. So this is a typical process for any new technology to be implemented by the industry. But the key question for me was, how long will it take? And in the case of the mining industry, it can take from 20 to 25 years. The mining industry is traditionally slower compared to any other industry sector in adopting new technologies, because the big players historically wanted to be very confident in technologies, and they let the small guys to do all the to take the initial risk, and they jump on technologies only when there was a good chance of success, which is fair enough. I mean, if you're not a risk taker, this was the attitude in the past. It is now changing, and I will say this in my next slide. And yeah, here is a typical situation when this is Max Zanin visiting a concentrator and trying to speak to the plant superintendent and asking him to read the report. they don't have time. They're too busy running the plant to spend the time to read the report, and maybe you have the solution there already waiting to be implemented. It happens very, very, very often. So who's taking the risk? As I said, that's my personal impression, but in the last couple of decades, the big players became more risk takers. So you can see big companies adopting technologies earlier than they used to do before. And if you read around on the press release, news around the mining industry, there is a lot of news about, as an example, Newmont installing iris flotation technology, which is stack cells at Chris in Canada. So an entire rougher bank replaced by stack cells. And again, hydrofloat installations here and there at Carapatina very recently in other parts of the world. And again, new Jameson cell installation by big mining companies. So a lot of things are happening and things are changing. So if it used to be 25 years, probably in the future, that time span will be narrowed and narrowed and narrowed, and we will see big mining companies adopting technologies a bit earlier than before. But, and before I conclude, this is also a very important thing to consider every time we think about new technologies. What can go wrong with the new technology? So one of the typical reasons why something can go wrong is that the plant scale unit is not performing as the pilot unit. So you develop a technology that at plant scale doesn't perform as in the lab. It gives worse metallurgical results for a number of reasons that we were not able to predict. So first reason for failure. Then there can be operating issues which are initially overlooked that become obvious only after you run the technology for several months. Because typically in pilot scale or lab experiments, you run just for a short time and you don't see those problems. They arise only when you run that technology for months. It happens very often as well. One other critical thing, operators. Operators are not adequately trained on the new technology. So introduce a new piece of equipment in the flotation circuit, but you don't train your staff. They don't know how to operate it at their best. And so you have some problem just because you're not running the equipment as it should be. There is a lack of troubleshooting, that may be a lack of troubleshooting procedures because there is no past experience. So you don't know how to fix problems when they arise. And maybe there is an easy fix, but it takes time before you develop those procedures. And also reluctant to change. Sometimes it is difficult to convince people to adopt something new because they've been used to the previous technology and they don't want to change just because they don't want to. So we need to consider all these things. So every time a new technology is introduced, a new culture within the organization needs to be developed. It is very important, otherwise it is a recipe to failure. But I want to add, and I added that quotation from Peter Monroe because I also strongly believe in this, which is the one in yellow here. He told me once, keep in mind that mechanical cells are always very forgiving, while other types of cells are not. And that's very true, because mechanical cells, as I said, they may be inefficient, and we know they are. But to say in simple words, if you don't get your minerals in the first cell, you may get it in the next one. So they are forgiving your mistakes. You stuff your front level, you stuff your chemistry for the first 2-3 cells of the bank. By the end of the bank, you may be able to adjust things and get your recovery anyway. So they may not be too efficient. It is good to replace mechanical cells with new technology in specific parts of the circuit where you can do that. But keep in mind that while mechanical cells tend to be forgiving, if you have the condition wrong in some of these other new technologies, it is more of a problem in the plant. So we need to consider both things when to decide if we want to go for mechanical cells or any of the other new technologies. Always take in mind that the old road sometimes is safer than the new one. All right, so we reach my conclusions. As I said, mechanical cells are reliable and easy to operate, but they are somehow inefficient, particularly for the coarse and fine particles. Significant improvements can be achieved by specifically targeting the hydrodynamics for fine and coarse particles. We need high energy, high shear for fine particles. We need quiescent environment for coarse particles. A number of promising new technologies is emerging with innovative approaches to flotation, different from mechanical agitation. But selection of cell type, design, and circle layout depend on several factors. So there is no best configuration which fits all. They need to be decided based on the specific ore and specific particle size that we want to treat. Due diligence is paramount. This is my final comment because it's very important to consider all the possible implication of any change you do to your plant before you start doing things. Otherwise, it's a bit of a recipe to disaster. And this is pretty much it. Thanks for listening, and thank you very much for your attention.
Oh, thank you, Max. I would open the floor for questions if anyone has one. Max used to be my supervisor during my PhD, and I was working mainly on the hydrofloat. And this was 2011 when I started my PhD. And at the time, there was no single hydrofloat cell installed in a copper or base metal plant. What, 16 years down the line, probably 40 installations somewhere else. So yeah, it's probably taking lesser and lesser time, and perhaps the mining industry needs to adapt to technology and innovation.
Thanks, Max. Lisa Forbes here. Great presentation.
Oh, hi, Lisa.
It's been a while.
Yes. Yes. By the way, I'm sorry. I really wanted to come in person this morning, but I couldn't because I had other commitment here. But I will pay a visit to you as soon as I can.
We are very much looking forward to that. Comment on Peter Monroe's comment about flotation cells, conventional cells being forgiving. This forgiving attitude comes at a huge cost of an enormous footprint. Because if you can rely on things being taken care of in the next cell and the next cell and the next cell, you're essentially sacrificing all the gains that were made specifically to reduce mineral processing footprints, physical, energy, and water. So do we actually have a proper sense of the cost of said forgiving attitude? That we can then make a judgment on whether or not we're prepared to pay it in favor of a more risky technology.
Yes, I mean, it's a very good comment, and it goes back probably to each person individual attitude towards taking the risk. So I believe you're right in what you say, because it's not too difficult to quantify what the cost is of not taking the risk, because you can do some maths about how much recovery you're losing by keeping your by sticking to mechanical cells versus how much you could get by adopting one of these new technologies. So you can have a dollar value of how much it costs you. But what Peter Manor was saying is that you also need to consider how much it costs to you when something goes wrong in the plant because your new technology is not performing and you need to stop operation for a couple of days to fix it, and how much time it happens over the year. So there is a balance between the two things. I believe that it really, once the technology is proven, we should move into these new technologies as fast as we can, but always bearing in mind that the old mechanical cell prevents some of the problems that you may have if the new technology goes wrong. That was the comment.
Any more questions?
So there's an online question from Juan Louis Reyes. He's asking whether, so he says, to mitigate short circuit, it is crucial to optimize cell design and operating conditions. This includes ensuring adequate mixing, adjusting airflow rate, and maintaining appropriate pulp densities. Is all of this well understood? and included in a large flotation cell that can mitigate the short circuit effect?
Well, yes, I can only say yes, I agree. It's a very good comment. It's very important to optimize things, in particular with respect to pulp chemistry when you're talking about copper flotation. So not only agitation and pulp density, but also aeration, pulp chemistry, and oxygen demand, DO and EH. Yes.
Hi, Max. Thanks for your presentation. Very interesting. I'm on the geology side. So my question is, of the issues with those new technologies, how much is a matter of better characterizing the minerals and rocks that we are gonna process, and how much is the technology itself? It's like if you do a very good job at characterizing all the particles and everything else, how much can this solve the issue with those new technologies?
Oh, well, very interesting question. And yes, I would say that it is very, very important. In particular, I'm now thinking at coarse particle flotation, so fluidized bed flotation, mineralogical characterization, and therefore knowing very well how liberated your particles are and what the exposure is of the different mineral phases. It is critical to help and assist on predicting or troubleshooting the technology. So I would see that mineralogy is very, very important, in particular for coarse particle flotation, and it may definitely help optimizing operations. Yes.
Thanks for the talk, Max. I'm Tom Evans, I'm a geologist as well. My question's sort of relating to technology uptake and scale as much as anything. A lot of what drives the decision-making process in the mining companies is, access to capital and how much people are willing to spend. So do these different new emerging technologies, some of which may operate better or worse relatively at different scales of implementation, do we see a sort of a bias because people are building smaller plants first initially and testing them out, and they may not be working as well as if they had just gone all in and built something larger and more efficient? Is that something that's, A, does it occur, and B, is it sort of captured and accounted for in the way that industry takes up these technologies?
Honestly, I understand what you say. It makes sense, and I think it is happening to an extent. But I don't have any personal example of situations like that. I mean, I can also see larger installation happening straight away. I mean, after some pilot work, and yeah, it is very important to consider because, as I said before, scaling up may introduce some problems that you don't have at smaller scale. So it's definitely a safer way to go. But I can't think right now of any specific example to bring to discussion. But it's a very good comment what you made. Yeah.
No, thank you. So it was a vague question from a position of ignorance, but
Thank you. Hi, Max. Nerida Scott from CSIRO. I just have a question about slide 6 where you had the elephant curve.
Yeah.
I've looked back in that reference, the Lynch reference. It's Lynch 1981, I believe.
Yes.
And I can't find that elephant curve anywhere. And so I wanted to ask you, and also the audience here, who drew the elephant? And I think that the data may have been from that book, but the elephant curve, that actual graph, isn't in that reference.
Okay, that's very interesting. It's new to me, but I will investigate then. I didn't know. I didn't know.
Thank you.
I think the elephant was actually introduced by Kominich. The elephant was introduced by, is it Kominich, recently? Yeah, so the yeah,
Okay.
so I've seen this in the Kominich article, but people do reference Lynch as well, but I'm not really sure.
Probably because the data come from Lynch, but
Yeah.
that's interesting. I really didn't know this. Okay, thank you.
Yep.
Hi, it's Tim Napier-Munn here. Max, thank you for the talk. One of the things you mentioned was AI and what you called advanced mathematics. I wonder if you could enlarge a bit on how you think those two capabilities will contribute to the future of flotation in its most general sense. And just to make a point, I read an article the other day that made a very persuasive argument for saying that AI is actually not very good at mathematics. So they may be two different things. Could you talk a little bit more about that?
Well, I can a little bit, but you're asking to one of the person who's a bit more skeptical about the application of AI to mineral processing. So I'm a bit biased against, but I understand that it is the way to go because everyone is going that direction. My concern is that, as you know very well, a mineral slurry, it's a very complex system. So it's very heterogeneous with respect to so many variables that even if you have the most powerful data processing unit, AI unit, it's very difficult to identify what's relevant to recovery rate and what it isn't, because there are so many variables which are not properly measured at the same time, because we all know that we have a bunch of data coming from plants which are not too reliable. So I've seen, for example, now working in the BRIEF consortium, that one of the most difficult parts in the application of big data analytics is cleaning the data. So removing all the data which are outliers, which are not correlated to the process before you can start any analysis of the data set. That's the most difficult thing. So applying advanced mathematics to bad data is not going to work. And so I understand what you say, and I agree to the fact that before you start talking about big data, you need to have good big data. And that's very critical in mineral processing. It's very different from other industry sectors. I'm thinking about car manufacturing. It's always the same thing. You have an engine, you have mechanical parts that you need to produce, while a mineral slurry, it's the most difficult thing I ever saw to model and to measure and to collect data from.
Thanks. I understand your answer. Just a small point. I'm always very troubled by this word cleaning the data, because actually the outliers often carry all of the new information. So it's a very troublesome business. And I do agree with you. It's a complicated system. So you hope that big data or AI or whatever it is will magically come along and sort it all out. And I think it will actually in the long term. But I share your concern that there may not be an easy answer lying there just at the moment.
Yeah, I agree.
Bill Johnson from Mineralis Consulting.
I will.
Pleased to hear your talk, Max. Wondering what you think of the extent to which companies contribute to their problems with implementing the new technologies. They really need to introduce limited amounts of the new technology into existing plants to supplement those plants, to get some confidence in what those that technology can provide and how easy or complex it is to operate. So I think it's also a management problem of how to introduce and get used to new technology, and you need to do it at a small scale and then later at a larger scale.
Yes, you are definitely right. I can only say I agree, yes.
Hi, Max. There's one from Nigel Smalley. So he said you did not mention the Woodgrove direct flotation cells. What's your view on that?
Oh, as I said, I only reported some of the new technology. I didn't report all of them. And the one from Google you're mentioning, I personally don't have too much experience with it, so I wouldn't be able to actually give you a sound comment. Yeah, I wouldn't know how to comment. Yeah.
And there are a lot of emerging technologies coming up as well in terms of coarse particle flotation. There's the Nova Cell. There's
Yeah.
Hips more, but most of them are in.
Yeah, but even the direct flotation cell from Woodgrove, I saw the basic principle behind it, but I never saw one in operation. This is why I can't comment. I understand the principle, which avoids the formation of a froth phase and gives you improved collision. But as I said, I never saw one operating, so I don't want to comment.
Yeah, a lot of the new cells are either in pilot or lab scale testing, and they don't really have full scale applications yet. So it might be difficult to. Anyway, in the absence of further questions, or are there more questions? In the absence of further questions, can you please join me to thank Max?
Well, thank you very much. Thanks for inviting me, and thanks for listening to my talk.
Next week, we have Dr. David Miljak from CSRO Mineral Resources talking about real-time sensing in mineral processing applications. So please do turn up as you did today. Thank you.
Thank you.